So hashing is something which is, in one sense, technically least understood in terms of the complexity. So all we can say is hashing is a data structure of some complexity. But the attempt here is to reach the complexity of order of 1. But we will see very shortly the way the hashing works. It's almost like black magic. And having seen the counting sort algorithm, you would appreciate hashing, because in the counting sort algorithm, it is somewhat of an hashing being used in the process of sorting. And in one sense, that counting sort algorithm is a hashing based sorting algorithm, as opposed to a search based sorting algorithm. So again, hashing is dealing mainly with dictionaries, and dictionaries, as we have introduced in the past, we are dealing with key and value pair. So objective here is to see if we can look up. So our objective here is to look up for a key in the dictionary with constant complexity. This is our goal for hashing. Okay, to motivate the problem, let's just think of for standard dictionary. The standard dictionary has got words. So when we are looking up a word, that is our key in the dictionary. So word acts as a key that addresses its definition. So when you are looking up the word, then you are able to see the several definitions, which are essentially the values associated with the word. So suppose I only have 2-letter words in my dictionary. So 2-letter words only in my special dictionary. Okay, let's see. So if it is 2-letter words, how many possible words are there? We are considering English alphabets here. So there are
26 squared.
Exactly. So there are 26 alphabets to choose from. So therefore it is 26 times 26, which is equal to 676 possible different 2-letter words. Now, do you think if you are having 676 possible choices, how many words can we think of that are actually valid words, valid 2-letter words? It's only a chosen few, correct? So actually most of the possible combinations are not actual words. In any case, 676 is not such a big number. So we can come up with an encoding mechanism. So we can come up with an encoding mechanism. So what encoding mechanism can we come up with? So you can see that there are 26 alphabet. So you have learned in one of the, the homework assignments that essentially all letters or all characters in the C++ language, they are essentially integers. They are the ASCII values, right? In fact, in your Linux or Unix terminal, you can do man ASCII. If you do man ASCII, it's going to bring up all the mapping, the integer mappings of all the characters. This is just a side point. So therefore, it's easy to see that there is every character if we take A as the beginning entry. So suppose my words are represented in the array of 2 letters. So char words. So then each of the word, so we take word 0 minus the character value of A. So this will give you the encoding. So for every letter, it's going to be put into 0 to 25 possible numbers. Essentially, this will map into this range, right? 0 to 25. So total number of letters are 26. So you can say 26 times this plus words of 1 minus A, right? So this is again the range of 0 to 25. So this will become a nice encoding given any 2-letter word, right? It's going to come up with a nice index. So suppose you are designing an encoding function. Let's call it hash code. Okay. And this hash code returns this. Okay. And this is, say, int hash code. So where is this hash code written? It's inside some class, let's say. And this class is the word class, let's say. And in the private section, you have essentially your definition char words. So suppose this is defined. Okay, so now you can see the big picture here. So this hash code, given any words, it can just find an encoding in the range of 0 to 675. So you can think of, so now what we have got, so what we have got is, we have got this whole going from 0, 1, 2, ... 675. So given any 2-letter words, it will map to a particular entry in this range. Okay. So in here, we can write essentially function like insert. So you can write void insert. And what will insert do? So insert is introducing a character, sorry. So this is not going to be here, but suppose, so essentially what I'm saying is, suppose you have another class called dictionary. And in this dictionary, you have, let's say, in the public section, void insert function. So this insert is getting called on the word W, and you are passing some value V. So what are you going to say? So you can say that my definition dot my definition W dot hash code is equal to V. So what is this? So this def is essentially some definition star definition def. So essentially this is what is the definition. So where every definition is taking the index, which is based on this encoding, and it is determining which is the address. And in that address, it is storing the value, which is which is essentially representing the definition of the word. Is this point clear?
Can you elaborate a little bit more on the hash code function? Like, can it just be any one-to-one function, or does it have to like output a sequential mapping? Or yeah, I was just wondering.
We're going to discuss the hash code in great detail. Right now, I just wanted to build the very simple case here. We're going to discuss about hash code in great detail. Right now, just try to understand that this encoding is a simplistic encoding. Given 2-letter words, it just maps into this range of 0 to 675. Okay. We're going to have elaborate discussion on hash code. First, let's try to see what happens in this simplistic encoding. Is that okay?
Yeah, that's good.
Yeah. Wait, sorry, just to clarify. So in that array of like the def tables, so the definitions are stored, like the definitions are not stored in there, right? But we're basically like indexing.
You can think of it like an array.
Right.
Right. I'm just calling, I'm just giving an abstract type here. Yeah. So where this definition is essentially taking the address value, right? And the index is being computed, taking the 2 parts of the word, right? And it's a very simple mapping. It just takes that, and then from that it subtracts the ASCII value for the starting.
Yeah.
which is A. That's all. Very, very simple. Okay, so this is the insert. So what is going to be find? So you have to look up. How would you look up? So you're looking for what? You're looking for definition. So looking for definition in the sense that you're looking for this entry, right? Whatever is there. I mean, right now we're just storing the probably the meaning of the word. So because this is the key operation that we are interested in as far as dictionary is concerned. You insert something, you find something, and you delete something. That's all. And as we have seen, other examples of data structures used to represent a dictionary. But hash tables are considered to be a great data structure of choice to try to reach the complexity of order of 1. And who would not like to have order of 1 complexity for search? So here, when you are looking up for a given word, right? So what should I be doing here? What should I write here? So I already inserted, you can see in a particular location in this.
Don't you find like the values in the array, like call it hash code or something?
Right, it's exactly this one, right? So I take the W, I find the encoding because that encoding is giving me the address, right? And I'm calling that on def. And this is what I'm returning. And I'm done. So what is the complexity for this lookup? All I'm doing is just hash coding and then indexing into the nice encoding table I have got, and then I'm returning the value. So this is clearly going to be order of 1. So constant complexity insertion, constant complexity extraction. So everything is order of 1 operation. So looking up, in fact, is as fast as possible, is extremely fast. Do you see any problem? What is the problem here?
There's a lot of space complexity.
Okay, correct. So in this case, all I have represented is only 2-letter words. So what is the situation of the real dictionary? So in a real dictionary, the longest word, anybody knows what is the number of letters in the longest word? 45 letters. And what does that mean? If I have to apply the same kind of strategy, how many entries would I need? 26 to the power 45. Correct? So 25 to store all possible words. But do you know how many words are there in a dictionary? Approximately?
Like 20,000.
700,000 in English dictionary. So you can see this strategy is extremely wasteful. And we cannot just generalize this. So what worked for 2-letter words is fine, but it's not at all practical. So we need to be able to operate on arbitrarily large words at the same time. Okay, so now we have to introduce what is called hash tables. So this is based on the conceptual notion which I just presented, but it needs to be much more refined than what I just presented. Again, the operations that we are interested in is insert, find, and remove. Okay. Okay, so let n be the number of keys, which is words in this case, that are stored. So number of entries, not maximum possible, but the actual number. So if it's a real English dictionary, there's going to be, like, if you want to be really comprehensive sort of dictionary, then small n is the 700,000, not 26 to the power 45. Okay. So now that is our small n. Now we need to determine what should be an ideal size of such a definition table that we try to design here. It cannot be such huge amount of space overhead. Therefore, we need to define something idealistic. So what we would like is a table of, let's say, capital N. This is called buckets. So we are introducing a new term. So each of the entry here, you can think of like a bucket. So this had 676 buckets. Okay. So we are introducing, so this is what is generally called hash table. Okay. So table of capital N bracket, where N, the capital N, is a bit larger than the small n. In other words, maybe about 20% larger. So 20% is okay. But still, this n is still way smaller than the total number of possible keys. And that is the key point. So we need to come up with a design in such a way that we want to incur the space overhead just minimally possible, not too much. Okay, so what is a hash table? So a hash table maps a huge set of possible keys into capital N buckets by applying what is called a compression function to every hash code. Okay, so what is the deal here? So the deal here is that we find some entry, right? So some entry comes. So let's call it a key. So you have a key. This feeds into something which is doing hash coding. Which is doing a hash coding, and this generates a hash code. Hash code. Hash code. So a key goes through hash coding phase, and this hash code then goes into what is called compression function. And this is finally generating the address to the, so you can say, bucket index. So this is the overall sequence that we need to have in order to create a hash table. Any questions so far? Okay. So essentially, this compression function is often referred to as H. So H on a hash code, you can think of the easiest hash code possible is, you can say, hash code, and then you take the modulo operator over capital N. And so naturally, this is going to generate 0 through n minus 1 addresses. And because of the representational limitations, this can even often become even negative. But that doesn't matter. So overall, the point is that you are taking a hash code, which can be something very obvious, simple, hopefully, and then this is the compression function. Okay.
I have a question about that. Using just the modulus operator, isn't that like not necessarily one-to-one? So like every unique hash code would not necessarily yield a unique like compressed hash code.
Exactly. Yeah. And that's why we need something else also. That's exactly what I was going to say. Just like you said, that it may generate duplicate entries, or what is known as collision. So therefore, this is likely to have what is called collision. So what do you do when there is a collision? So first of all, collision, let's define it formally. Collision. So what is a collision? Where several keys hash to the same bucket. And that is possible if h of a hash code 1 is equal to h of a hash code 2. And that's exactly what you're saying. So natural question is how to deal with collision. So first of all, let's ask ourselves the question, how to deal with the collision, and then we will talk about how to make sure that we are reducing the collision. Okay, these are two different topics. So first is how do we deal with the collision. So when there are two, so this is our first question. When there are two hash codes mapping into the same bucket entry, what can you possibly do? Any ideas? So there are different techniques that are there in the literature. Two common ones are called, one is called chaining, another is called probing. So for this course, we'll just discuss the chaining technique. And even in our assignments, we'll try to apply the chaining technique. So chaining. So what is a chaining? Where each bucket points to, so chain is what? It's a linked chain. So it's a linked list. So linked list of entries called a chain. And it stores both words and definitions. In the chain. So every entry is essentially key value pair. Okay, so how it would look like? So this is your definition. Definition table. So definition table will be essentially pointing to the whole series of buckets. And wherever it got mapped to, it will have, when the first entry comes, it will point to some key one, value one pair. And again, the second entry later on, it may point to, let's say this is key two, value two pair here. Another entry comes, it may point to K3, V3 here. And then K4 somehow or other map to the same location. So what we are going to do, we're going to form a linked list. So the K4, V4. So you see how it is organized. So now you can imagine if our compression function and hash coding mechanism somehow leads every single entry to only one bucket, then what's going to happen? Then the search complexity will degenerate into the linear order of n, right? Because all the entries have just formed a linked list. So when you're looking up, you've got to this entry and then you are just traversing the linked list to find the match for the key. So that's the worst possible situation. So the ideal situation that we are expecting is that our hash coding mechanism, our compression function should be so good that we get a perfect distribution of the keys in this definition table. And that is why I said in the beginning, hash tables is a kind of data structure which is like black magic, because all the magic is in how you're doing the hash coding and coming up with compression function to minimize this kind of collision. So the effectiveness of the collision avoidance is dependent on the properties of the hash coding and compression function.
Wait, sorry, just to clarify one thing.
Go ahead.
So the K1 V1, right? For
Mhm.
example, like those store like not just the definition, but also the key, but we're just basically
It's a
organizing
node.
keys into buckets.
It's just like a node, right? When you are storing in a binary search tree, what do you store? You store the whole object, right? This is like an object you can think of.
Right. But like, for example, can you give like an example of a bucket, like in this, like a simple example, maybe?
So you mean to say example of what is a key and a value? I mean, what do you mean by example of a bucket? I mean, bucket is just you can see simply pointing to the head of the list, right? Every bucket entry is like a head. I mean, pointing to the head of the chained list of entries that have mapped because of having the same compression address, or after going through the compression function, they resulted in the same address.
But like, how is the order of the buckets like determined in relation to the key value, for example? Like
Ordering of the buckets, you said?
for example, like if there's a word, I don't know, like ant and like apple or something, like
Yeah. So if there is
the
an and,
buckets like, I don't know, based on that first letter or like.
so and for suppose after going through the hash coding, right? Some hash coding that you have come up with, whatever that is, you came up with a figure, let's say 15. Okay, this map to 15. Now this 15 goes through the compression function and comes up with a value, let's say 6. So it's going to go into the sixth entry here. Is that clear?
Oh, and you're saying like
And
when we
then
take the mod of numbers, like several numbers could become 6.
exactly. So that's exactly
Oh.
what we said here, right?
Okay.
When we are doing compression function on the hash coding, so different varieties of entries have come up with different mappings to the hash coding, right? Whatever the scheme is. And this hash coding, then when you're compressing it, now the question of collision comes. Clear?
Yeah, that makes sense. So when we get the same compression code, that's when we add.
That's when that's when we end up in a collision situation, and then we are just creating a list of those entries.
Okay, makes sense. Thank you very much.
Very good. Any other question before I move forward?
Yes, actually, I have two. The first one is, do you actually also want to avoid it that you don't have any collision at all? Is it like, when you don't have any collision, does that mean that you're not compressing the other possibilities into n?
So first example that I gave was basically zero collision, right? Example.
Yeah.
And you can see what is the situation here. So zero collision means you are ready to pay infinite amount of cost, practically speaking.
Okay.
So you're not wanting to pay. You just want the bucket size to be just a little bit above the number of valid entries, and that's where the problem begins. You know, that you keep the space overhead to the minimum. So how do you manage that?
So you want, I see the point that some getting together but not getting in the exact same spot. And with can you explain the and hash code and H again? Do you do the hash coding twice? Is that? what you're trying to.
No. So ant is a string, correct? The string needs to be somehow mapped to a value, right? So here, when you have a 2-letter words, right? We came up with an encoding mechanism here. So in this case, our encoding as well as compression, we didn't do any compression as such. We just did encoding. We just did hash coding, right? And we had enough amount of buckets to store all the hash code. And therefore there was no compression. So this is the first example that I started off with. I just showed, okay, you did some hash coding and you didn't need any compression because you have enough space. But the moment you go into really a large number of possible options, you have to think about compression. And then you would have to think about how we are going to map to this much smaller number of entries that are there, or much smaller number of buckets that are there than the overall number of possible possibilities. Like in the case of dictionary, right? You have, like, if you look at the possibilities, right? If you apply the same kind of hashing technique, right? Hash coding technique that we apply to the 2-letter word, right? And we are applying to the largest possible word. So then there are 26 to the power 45 entries that are possible, correct? After hash coding. But that's really ridiculous. So that doesn't make sense. So you need to have a hash coding mechanism, and then you need to have a compression mechanism where you're storing these 700,000 words in the number of buckets. Maybe you are choosing to have 1 million and not more than that. So it's slightly bigger than the total number of actual words possible, not total number of all possible words. That makes sense?
Yes,
Alice?
it makes sense. Yes, it makes sense.
Okay. Yeah,
Thank
that's why I started with a very simple example, just so that you can now appreciate the need for compression. Okay, so now let's look at the operations. By the way, the topics that we are discussing today is are the topics of topics which are favorites for all the interviews that happen in the world of computer science. They love hash tables, they love graphs, you know. So please pay close attention and try to follow every single thing. Okay. Try not to leave anything ununderstood or okay, so now here, the first thing we want to do is insert. So we want to insert key and a value. So what do you do for insertion? You compute the keys hash code. And then you do compress to determine the bucket. And then you insert the entry into the buckets chain. Okay. Second operation we are interested in. So entry find. Let's put it pointer. So you're trying to find a key. So you can imagine the first step is, as usual, you compute the keys hash code. And then so search, so hash code and bucket. So these two steps are common, okay? So this is the same step we are putting in here, okay? No difference. Then you search the chain for entry with the given key. So now you're looking down in the linked list to find whether there's a match in the key. So if found, then return the entry. Otherwise, return null. Okay, the third operation is remove. So you want to remove a key. So again, hash. So from now onwards, when I say hash key, it just means you're applying hash coding and then compression. And then you search the chain and remove. So this is like linked list removal, right? So remove the entry from the chain. And so either you may not find it. So either you return the entry or null when it is not found. So one key question can be asked that what if there are multiple copies of the same key? So it depends on the application. This question is very specific to the application. What do you do? There are two possibilities. Either you insert both. And if you have inserted both, so this is the, by the way, in the world of the standard library, the hash tables generally map to std : what is called unordered map. Okay, this is the hash table implementation. So in the map, there can be multi-map or just map. So multi-map means where you're allowing multiple copies of the same key to exist. Okay, it's just some detail. So when there are multiple copies, so either you can deal with it in this way, that either insert both and then find can return arbitrarily one. So arbitrarily one of them. Okay. The other possibility is that you replace the old value with the new. Replace the old value, right, with the new. So that's why I said it depends on the application. So then this will only have one entry only. Okay. Any question on that? Okay. So now let's discuss the performance of a hash table. So performance of a hash table is a complicated subject. So we're going to summarily present. So the performance of a hash table is measured by what is called load factor. Okay. So load factor of a hash table is defined as the small n, which is the total number of actual entries that are possible, like the possible number of keys, right? And by the capital N, which is the number of buckets. So number of keys and number of buckets. So if the load factor stays low, so low meaning close to a small constant. So generally a good load factor is going to be approximately 0.8 or 1.2. That's the range in which a good load factor remains. So that's what we mean by close to a small constant. So two things. So if the load factor stays low and hash code and compression function are good. Okay, hash code and compression function, they're good. And no duplicate keys. Then we can say then the chains are short, and as a result, each operation takes constant time. Okay. So if the load factor gets really big. So really big, when can it get? When small n is much larger than capital N. Okay. In other words, the number of keys keep growing. So number of keys here, again, assuming that there are no duplicate keys. So number of different keys here. So number of different keys keep growing to such an extent that it has become really much bigger than the bucket. Then it will end up in order of n time. So typically you can think in this way. So if n is big, right, which means that the bucket size is really huge, then the cost is to set it up. Uses a lot of memory. On the other hand, if small n is really, really small, then the load factor is really huge, as a result of which the performance will be hit tremendously. So this is the situation we have. Okay, so now, therefore, naturally, our part 2 of the discussion. So far we talked about how to deal with the collision, right? That was our number 1 question. How to deal with collision. So now we have to discuss how to minimize collision. Okay. So in other words, we want to discuss how to have a good hash code and compression function. So how to have a good okay. So typically hash codes can be harder, and compression function can be as easy as just taking a modulo. I'm hoping that everyone here in the audience understands the modulo operator, because this plays a big role in the quality of the hash function. So this, if you have some introduction to number theory, that would be really fantastic. If you've gone through the remainder theorems and appreciate the value of prime numbers and so on and so forth. So overall, everyone understands at least what is mod operator, because a little bit of understanding would be necessary in order to appreciate what is a good hash code and what is a good compression function. Okay, let me ask in a reverse way. Is there anyone who does not know what is a mod operator? Okay, good. Then we can move forward. So key, as I said, we want to get to the hash code, and the hash code we want to get through the compression function, which we already indicated that.
Oh, Partha, sorry to interrupt. Looks like one person put in the chat. They're not familiar with modulo.
Okay. So very quickly. So modulo typically means when you divide with something, what is the remainder? So suppose I want to put the values in a particular range. Let's say I want to put everything in a range of 0, 1, and 2. So how do I do this? I can divide some value n, which I'm interested in pushing into this range. I want to divide by 3 and then take the remainder, because the remainder is going to range in this this range, right? So modulo means when you divide. So if I say n mod 3 is the remainder when n is divided by 3. So you can imagine, therefore, if I have to fit everything into the bucket size of n, what are we going to do? The moment we say modulo of n, that makes sure that everything is just fit into that size. Is that clear? So whatever the hash code is, as soon as they take the when I take the hash code and I say mod of n, it puts me in the range of 0 to n minus 1. Just like we saw, when you take any number let's say 5. So when you do mod 3, what do you get? You get 2. So in this way, you can put any number, 17, mod 3. What do you get? You get 2 again. So in this way, you can see anytime you want to actually put something in a range, you just apply this remainder. Is that clear? And taking the modulo, especially with prime numbers, can have the scrambling effect.
Thank you.
Okay. So you take a key. So from there, we get the hash code on which we apply the compression function, and we get the range 0 through n-1. This is the scheme we want to have. So this is the overall scheme. And now we have to go step by step, and let's talk about what is the ideal. So ideal is that I want to be able to map each key to a random bucket. So this randomization is key here. So the more random and more uniformly distributed through the bucket, the better it is. So you want to map every key to a random bucket for fewer collision. With each bucket being equally likely. So if you are able to get to this equally likely situation, then we will have a very good distribution. Now, because we are talking about black art here, so we can talk about bad designs, but it is difficult to explain why something good is really good. We can talk about why something is bad, but it is very hard to reason about why something is really good. So what is really good has been proven to be empirically good. That's how the story of the hash functions is in the overall community. Therefore, let's discuss how do we evaluate something as bad, okay? So what would be a bad compression function? Okay, so suppose, so we are going to first talk about the bad compression function, then we'll talk about the bash hash code, okay? So suppose keys are all integers. Okay, suppose everything is integers. And one obvious hash code would be hash code of I is essentially I, which is the same as the number itself. And suppose the compression function that gets applied to the hash code, we come up with a compression function, something like this, is equal to hash code, very obvious compression function. This is the most obvious compression function one can think of, modulo n. Just like I said, if you want to fit within the n buckets, just take modulo operator, and that's going to generate the values 0 through n-1, and we are done. Isn't it great? Okay, let's see the situation here. So suppose the total number of bucket, which is capital N, is equal to 10,000. So you have 10,000 buckets. Okay. And also suppose the keys happen to be all divisible by 4. So if keys are divisible by 4, so naturally when you're taking the keys and you're just applying I, so clearly the hash code is divisible by 4. And when you are taking modulo n, right, that is also divisible by 4, 10,000. So h of this is also divisible by 4. And what does that mean? So h is also divisible by 4. This means that 3/4 of the buckets are never going to be used, right? You're only filling up the slots which are divisible by 4. So is it a good compression function? No. So just taking a simple modulo n is not making it a good compression function. So the same compression function so it can be made better, if we apply a very simple trick. And the trick is that n is prime number. So then the better compression function would be this, that you take the hash code. So remember, we are talking about compression function. So h represents our compression function. So h of hash code is equal to a times hash code plus b. And on that, you take a modulo operator of a large prime. Okay, you take a modulo operator of a large prime, and then on that you apply a modulo operator of capital N to just fit within the buckets. So here what we did is that by applying this modulo P, okay, so here let me just be sure. So A, B, and P, they are positive integers, and P is a large prime. So P is actually much larger than N, which is also a so in this case the N need not be prime. So this we basically generalized it. So here N need not be prime because of using this intermediate scrambling. So this actually brought about the scrambling of the bits by applying this modulo P. Is that clear? So what?
Sorry, can you clarify why you multiply by A and then add B? Like it makes sense that you take a mod of a huge prime because like then you it's hard to like factorize a huge prime, right? But like why do you multiply?
Yeah, this is just creating some variety, you know. You take a positive integer, multiply with the hash code plus another positive integer. You created some sort of encoding, right? And then you want to scramble it further. by using a mod p. And this allowed you to not worry about this. So now here n can be 10,000, no problem, because of this scrambling that you just did with the large prime. So here, basically the sequence in which I showed is that the first is that we showed that if you have just a naive approach, just doing a mod of n, right? This is not going to be a great compression function. So to solve that problem, one simple approach you can take is that make n prime. So the same compression function can be better if n is prime. But if you want to just generalize it where n can be any number, it doesn't have to be prime, then you need to bring something, a larger prime here to bring about a scrambling, and then you apply the mod of n. Is that clear?
Yeah, thank you.
Okay, so what we have achieved here is that the number of buckets does not need to be a prime. Okay. Okay, so now compression function we are settled. Now let's talk about hash codes. What could be a good hash code? So a good hash code for strings, I'm just going to give you a very popular hash coding function for string. So you do int hash code, and then let's say this takes string. So this is our, you can say std : string key, and then you start with hash code, let's say hash value as 0. Remember, here we are doing just the hash coding. After that, we will be doing the compression, which we already discussed how to do that. So here we are just talking about how to do hash coding of a string. For integer, we just showed that, okay, a simplistic way of hash coding an integer is just map it to the same value, right? So there is nothing to discuss there. So what makes it interesting is that how do you go from a string or a set of characters to a hash value? What would be a good hash coding? That's what we are discussing right now. So we want to be able to somehow mix the bits. That's what we want to do. So you initialize hash value to 0, and then you run I equal to 0, I less than the length of this. And then plus I. And you do hash val equal to 127 times hash val. So this, you can see that there is an accumulation going on here. Okay. So first time you're entering the for loop, the hash value is 0. Okay. And then you're adding the first letter, right, in the string. So key of I is the first letter when I equal to 0. So it's going to be hash val equal to the first letter. And then the next time it comes, it's going to be multiplying the 127 with the previous value of hash val, and then adding the current value of the key. Okay. But that's not the only thing. So now here it needs to bring some scrambling effect by using a large prime. So here's an example of a large prime. So 1 6 9 0 8 7 9 9. Okay, I'm just giving away a common prime number that can be used, and you have accumulated this, and then you've got nice scrambling effect, and now you're ready to return the hash val. Okay. And this particular hash coding, it seems to work well in practice. That's the only thing that can be stated about this. That's because you can't find a flaw in it. So let's try to find some flaw so that you understand what does it mean by finding flaw. So what would be some example of bad hash code so that you can appreciate a good hash code? So what would be a bad hash code?
Wait, sorry, just to clarify one point. The 127's like kind of arbitrary, right? That's just
Not fully arbitrary. You're going to see very shortly. I'm going to take some examples.
okay.
Okay. So 127 is, I think, commonly used because of the range of the ASCII characters as well. And 128 is a power of 2, which is really, really bad choice. So let's take some examples. Okay. So overall, the question of bad hash coding has to do with creating some sort of, whenever there is a creation of biases in the data, that's when the hash coding becomes really corrupted. So different ways the biases get created in the choice of the function. So let's say what would be a possible bad hash code. So you can sum, let's say, ASCII values. So here we are talking about bad hash coding of what? Bad hash coding for strings, okay? We are not talking about integers because there is nothing to discuss about integers. So the keys of type strings, okay? Clear. So string keys. Okay, so some ASCII values of characters. What's the problem with this? Suppose your hash coding technique is just take the sum. What's the problem? And when you sum it, it is rarely, if you take the English words, it's rarely going to cross 500. And as a result of which, what happens? Most of the entries will remain kind of, most entries remain bunched up or mapped into these small set of buckets. So it's a very bad choice. And typically the anagrams like pat, then apt, tap, they will all collide, right? So anagrams will all collide. So therefore, this is not a very good choice. Let's take another example. What if you take the first 3 letters of a word with 26 to the power 3 buckets? What's going to happen if you choose that? So we know that there are biases in English language. What kind of biases are there? There are a lot of words with prefixes of pre, right? Even pro, etc. So there are, the first 3 letters are very, very biased sort of choices, and therefore, and at the same time, no word begins with prefix like Z, X, P or something, So there are biases in the English language, and therefore this will result in lots of collision. So very poor choice. Third example of a bad hash function. So suppose we change in the above hash coding prime modulus to 127. So all we are saying is that instead of having this gigantic prime number, what if we had 127 instead? What's going to happen? Would 127 here would be a good choice instead of this prime number? So you can see what's going to happen. First number, I mean, every number we are multiplying with 127, right? So when you take modulo of the same, so we know that when something is divisible by the number that we are taking a modulo operator in, the remainder will be 0, right? So this is not going to play any role, right? So it ends up in just summing up the you're only doing basically 0 plus the last character, right? Everything gets kind of zeroed out because of this. So you will end up having everything mapped to key of the key of length, key dot length minus 1. Is that clear? So therefore this is not a very good choice. So if you took 127 multiplied by hash val multiplied by hash val, and you take the modulo operator, this percentage is a modulo operator in the C++ language, right? So when you take 127 equal to 0, sorry, y double equal to, this is equal to 0. So therefore this will end up in only the last character in the hash code. So you can see that we can reason about why certain function, hash coding function chosen is not good. Okay. But it is hard to talk about why a good hash function is really good. You can reason about to some degree, but you cannot theoretically establish that that's going to be having the order of 1 complexity. So its order of 1 complexity is just in practice, that's all. So just one last topic in this is resizing of the hash table. Any question before I move on? Okay, one of you had question about the compression function in the beginning. I hope that question got answered now. Okay, let's talk about resizing hash tables. So if the load factor, which is n by capital N, gets too big, so what can we do? We lose the order of 1 time. So what should we do? So here are some strategies we can take. One is that we can enlarge So we can enlarge the hash table. When n by n, the load factor becomes greater than some constant, and this constant can be 0.8 or 0.75 or something like that. Okay, so if the load factor becomes greater than 0.75, then that's the time we have to think about resizing. So what do? We allocate. So we have to allocate completely a new array. And one common strategy is at least twice as large. Okay. And then you have to walk through the old array, right? Or you can say the old definition tables. That's what we were using, right? So this is our def table, right? So you go through the old def table. Then rehash. So rehash entries, because the n, capital N, has changed. So you have to rehash entries into the new hash table. So this is an overhead that one has to go through. You cannot just simply copy. You cannot simply copy from old chains into the new table. Okay. So that's because compression function changes and therefore entries go into. So compression function change. So it goes into, so entries go into different buckets. So likewise, what happens if n by capital N actually becomes less than 0.25? Then also it's not good. So one can actually shrink the hash table to free up the memory, some memory. So the point is that whenever resizing is happening, an operation can take order of n time, but that is not very frequent. Therefore, overall amortized over a period of time, the cost of resizing becomes kind of irrelevant. Okay, but at least you should know that overall one can take this this step of resizing as necessary when the load factor either becomes too big or it becomes too small. Any question on the hashing so far? Because this kind of concludes my discussion on hashing. And we're going to talk about graphs for another half an hour before we move into labs. Any question? Okay. So as I said, hashing